Good evening, dear students. So in the last class, we were discussing the MCQs based on the topic thermodynamics. Okay, so let us continue. So in the last class, I have completed the synopsis also on this topic. Okay. So we have completed few questions. Okay, almost 13, 14 questions. Okay, so let us continue from here. Yes, so this was the last question which we have solved. Okay, so here. So the question is, a spontaneous reaction is impossible if A, both delta H and delta S are negative, B, both delta H and delta S are positive, C, delta H is negative and delta S is positive, D, delta H is positive and delta S is negative. So when a reaction is spontaneous, so when the spontaneous reaction is impossible. So what are the conditions for a spontaneous reaction to be impossible? So what is the answer? So for a non-spontaneous reaction, yes, so a spontaneous reaction is impossible. It means what? So for a reaction to be non-spontaneous, what is the condition? What is the condition applied? So whenever a spontaneous reaction is impossible, if so we know that delta G is equals to delta H minus T delta S. So from this particular equation, okay, so your delta G will be positive. So when delta G will be positive for a reaction when it is a non-spontaneous reaction, okay. So that time your delta H also should be positive, okay, and your delta S should be negative. So for a reaction to be non-spontaneous, so these are the condition. That is delta H is, should be positive and delta S is negative. So option number D is the answer. So a spontaneous reaction is impossible if your delta G, that is, it is positive, okay, for a non-spontaneous reaction. So that time your delta H will be positive and delta S will be negative. So this is the condition. So this is a condition for a non-spontaneous reaction. Okay. So next question. The enthalpies of elements in their standard states are taken as zero. The enthalpy of formation of a compound. Options A is always negative, B is always positive, C may be positive or negative, and D is never negative. So enthalpies of an element in their standard states, they are taken as zero. So what will be, so if the enthalpies of elements, okay, when they are in their standard state, if it is taken as zero, so when you're forming the compound, okay, when you're forming the compound and when you're finding the enthalpy of the formation of a compound, so what will be the value? It will be always positive, always negative, maybe positive or negative, or is never negative. Yes. So for enthalpy, change in enthalpy is given as delta E plus delta Ng, that is mole of gas into RT, okay, nRT, number of moles of gas into RT. So this is the equation. So if, okay, so if N, so number of moles of the product, okay, if it is less than number of moles of the reactant, so that is delta G, that is your number of moles of your gas, okay, is equal to products minus number of moles of the reactant, should be always negative, okay. So for your delta H, so if the delta H what it will be? So delta H will be, if your delta G naught is negative, okay, so what should be delta H? Delta E, it should be less than delta E. Okay, so your delta H should be less than delta E. So it is never negative. So enthalpies of element in their standard states, okay, they are taken as zero. So when you're forming the compound, when you're doing the formation of a compound, okay, so how the compound is formed? So products will give you, that is reactants will give product. So your number of moles of product should be always uh, less than the number of moles of reactant. So that is the change in number of moles of a gas is equals to number of moles of product minus number of moles of reactant. Okay, so this, if this is negative, so your delta G E should be less than your delta H. So it is never negative. So enthalpies of formation of a compound will never be negative. Okay. So yes, option number D is a answer. The correct relationship between free energy and equilibrium constant K of a reaction is. What is the relationship between the free energy and equilibrium constant? How it is given? Do you know the equation? It is already derived in the, when we are solving, okay, when we are seeing the free energy and the energy equilibrium constant, okay. So how the this is given? What is the relationship between that? What is the relation between the free energy change and equilibrium constant? It is given by which equation? It is given by Nernst equation. Remember, it is given by Nernst equation. What is the Nernst equation? E is equals to E naught minus RT by NF ln of Q. So this is the equation which tells you the relationship between the free energy change and equilibrium constant. Okay. So we know that at equilibrium, okay, at equilibrium, your EC, okay, EC, that is the equilibrium constant, will be 0 and Q will be equal to what? QC, KC, right? So at equilibrium, what will happen? Your equilibrium constant, it is 0. So your Q will be equal to KC. So, uh, so therefore, E naught is equals to, so your E naught will be, so E will be 0. So E naught will be equal to RT by NF ln of Q is what? KC, right? K. So it is your equilibrium constant. So now we know that delta G naught. What is delta G naught? Delta G naught is equals to NF E naught, right? So if you put this equation, if you put this value of G naught, okay, here, so what it will be? So here delta G naught is equals to NF E naught. Okay. So put this in your equation 1. So minus, so what is E naught from here? E naught is equal to, E naught is equal to minus delta G naught upon NF, right? So put this value. So this will be minus delta G naught by NF is equals to RT ln of K by NF. So therefore, delta G naught is equals to minus RT ln of K. So what is the equation? So delta G naught is equals to minus RT. So NF get cancelled. So delta G naught is equals to minus RT ln of K. So which is the equation? Which is the answer here? Option number A. So this is a relationship between free energy and equilibrium constant. So how we got this relationship between free energy and equilibrium constant from Nernst equation. Okay, from Nernst equation, we have got this particular relationship, that is E is equals to E naught minus RT by NF ln of Q at equilibrium. Okay, when we see that EC is equals to 0, your Q will be equal to Kc, that is your equilibrium constant K. Okay, so therefore E naught is equals to RT by NF into ln of K. So we know that we know that delta G naught is equals to NF E naught. So if you substitute the value of E naught here from this, we are going to get this relationship. So this is the relationship between the free energy and equilibrium constant. Okay. Yes. So option number A is the answer. Let us go for the next question. 1 mole of an ideal gas at 300 Kelvin is expanded isothermally from an initial volume of 1 liter to 10 liters. The delta E for this process is, so R is 2 calories per mole per Kelvin. Okay, so options are given. So 1 mole of ideal gas is taken. Okay, and that is expanded. Okay, isothermally. So that is from an initial volume of 1 liter to 10 liters. So what will be the delta E? Okay, what will be the delta E for this process? Yes, what is isothermal? For this, you need to know what is the isothermal process first. Yes, what is the isothermal process, students? What is the isothermal process? You are keeping the temperature constant, right? So 1 mole of ideal gas at 300 Kelvin, okay, it is expanded isothermally from initial volume of 1 liter to 10 liters. So they have asked what is the change in delta E, okay? What is the change in delta E? So what will happen? Because the temperature is constant, your delta E will be 0. Okay, change in energy, it will be what? For this process, it will be 0. So option number B. For an isothermal process, delta E will be always 0. Okay, it will be always 0. So option number B is the answer. So isothermal process, what happens in isothermal process? The temperature is kept constant. Okay. Next question, the entropy change in the fusion of 1 mole of a solid melting at 27 degrees Celsius, latent heat of fusion 2930 joule per mole is. The entropy change in the fusion of 1 mole of a solid melting at 27 degrees Celsius, latent heat of fusion is given as 2930 joules per mole E. So you have to find the entropy change when you are fusing 1 mole of solid which is melting at 27 degrees Celsius. So entropy change, okay, it is given as latent heat of fusion by melting point, okay, upon the melting point, that is given as latent heat is delta H, okay, and a melting point is your temperature. So what is your change in this? What is your latent heat of fusion? It is 2930. And what is the temperature? Temperature is 27 degrees. So 273 plus 27 is 300. So converted into Kelvin. Okay. So degree Celsius is converted into Kelvin. So it is 300 degrees Celsius. Okay. So what will be the, so it is Joule, Kelvin. Okay. Joule per Kelvin and per mole. So this is the, your units. Okay. So calculate, after calculating this, what you're going to get? 293 by 30. So the answer, what I am getting after solving is 9.77 joule per Kelvin per mole. Okay. So this is the answer. That is, this is a entropy change. Okay. This is a entropy change, 9.77 joule per Kelvin per mole. So this is the entropy change when you are fusing 1 mole of a solid melting at 27 degree. Okay. Latent heat is given. So what is the change in entropy? How it is given? Latent heat of fusion upon the melting point. So melting point is given, latent heat of fusion is given. Just substitute and get the answer. So option number A is the answer. Okay. So the values of heat of formation of sulfur dioxide and sulfur trioxide are minus 298.2 kilojoules and minus 98.2 kilojoules. The heat of formation of the reaction Okay, the reaction is given as SO2 sulfur dioxide plus half O2 giving you sulfur trioxide will be. So you have to find the heat of formation. Okay, when SO2 and SO3. So heat of formations are given. So the reaction is given. So what is the value? So heat of formation of this particular reaction. So the heat of formation of individual SO2 and SO3 are given. Okay, you have to find the heat of formation of the complete reaction. That is when sulfur dioxide reacts with half O2 giving you sulfur trioxide. So this is a reaction. Okay, the values are given. The heat of formation of sulfur dioxide is minus 298.2 kilojoules and for sulfur trioxide is minus 98.2 kilojoules. Yes, SO2 plus half O2 giving you SO3. So the heat of formation is given as delta H is equals to delta H naught minus that is of SO3 minus delta H not F of SO2. Okay. So what is the heat of formation of SO3? Minus 98.2 plus, okay, minus and minus will become plus 298.2. So what will be the answer? It will be in kilojoules. Okay, it will be in kilojoules. Find out. 200. So it is 200 kilojoules. Okay, it is 200 kilojoules. So which is the answer? Plus C. Option number C. So values of heat of formation individual are given. You have to find the heat of formation of the reaction. Is it clear? Is it clear up to here? Okay. Let us go for the next question. What is the enthalpy change for? So a reaction is given. Enthalpy for a change for a reaction H2O2 liquid giving you 2 water plus O2 gas. Okay. So heat of formation for H2O liquid and H2O2 and H2O. Okay. The heat of this is given formation. This is minus 188 and this is minus 286 kilojoules per mole. So values of heat of formation of both the hydrogen peroxide and water are given. So you have to find the enthalpy change. You have to find the enthalpy change. So the reaction is 2H2O liquid giving you H2O plus what do you have to find? You have to find the change of enthalpy. Okay. Change of enthalpy. That is delta H. So change of enthalpy, it is given as what? So you have to calculate the you have to add the heat of formation, right? So what is the reaction? 2H2O2. So multiply 2 into H2O2 value is, so that is of delta HF of your H2O, okay, liquid plus your O2, okay, delta HF of O2. So this is your products, that is delta HF of products minus delta HF of reactant. So minus of 2 into delta HF of H2O2. Okay. So put the values. So 2 into delta HF of water is how much? Minus 286 plus O2 is 0. O2 is 0. Okay. Then minus 2 into what is that delta HF heat of formation of your H2O2 is minus 188. So substitute now. So I've put all the values. So 2 into minus 286 plus 0. So this becomes 2 into minus 286 becomes 2 8s are 2 6s are 12 2 8 is 16, 17, 2 2 is 4, 5. 572 minus 572 plus 2 8 is 16, 2 8 is 16, 17, 2 1 is 2, 3 plus 376 minus 572 plus 376 is how much? Minus 196 kilojoules per mole. Okay. So what is the answer? It is option number A. Option number A. Okay. Is it clear? So enthalpy. So heat of formation values are given. You have to find the enthalpy change. Enthalpy change, we have the formula. So after substituting the formula, the values, okay, we have got the final answer as minus 196 kilojoules per mole. Is it clear up to here? Yes. So enthalpy change, if they have asked, okay, and heat of formations are given. So like this, you are going to solve it. Okay. Okay. What is the entropy change? Okay. Now they have asked entropy change. What is the entropy change in joule per Kelvin per mole when 1 mole of ice is converted into water at 0 degrees Celsius? Okay. Ice is converted to water at 0 degrees Celsius. The enthalpy change for the conversion of water, ice to liquid water is 6 kilojoules per mole at 0 degrees Celsius. So these are the four options. So how we are going to find the entropy change? Entropy change with respect to when your 1 mole of ice is converted into water. So we know that entropy change is equal to change in enthalpy upon temperature. Okay. So they have asked per mole. So entropy per mole, okay, is equals to entropy change per mole upon the temperature, right? So what is the change in enthalpy? Change in enthalpy is given. Enthalpy change is given 6, right? 6 kilojoules per mole. So it is 6,000. Okay, 6,000. We have converted kilojoules to joules. So it is 6,000 divided by what is the temperature at 0 degrees Celsius? 0 degrees Celsius. When you convert into Kelvin, it will be 273 Kelvin. So it is 273. So find the answer. Find the answer. So this is the entropy change. This is the entropy change. Got it? So after solving, okay, I have got 21.98 joules per Kelvin per mole. 21.98 joule per Kelvin per mole. 21.98. Option number A. Option number A. So entropy change, it is given as change in enthalpy upon temperature. Okay, fine. Let us go for the next one. If the bond energies of HH, BR, and HBr are, so the bond energies are given of HH, BR, and your HBr. So what is the bond energy? 433.192, 432, not 192, 432, 433. This is 192 and this is 364 kilojoules per mole. Kilojoules per mole. Okay, kilojoules per mole. So you have to find the, what you have to find? You have to find the heat of formation. Okay, so delta H for the reaction. So the reaction is given as H2 gas plus Br2 gas will combine to give you 2HBr. Okay, so find out what is delta H. Delta H naught. Yes, delta H naught. So delta H naught is what? Okay, so bond energy of reactant minus bond energy of product. Okay, so delta H naught. So what is the bond energy of reactants? Reactants are your H2 plus Br. What is 433 plus 192? Okay, minus product is HBr. So 364. Find out 2 into. Okay, you have 2 here. So 2 into 364. 5, 9, 10, 11, 12, 5, 6. 625 minus 625 minus 728. Okay. So after solving this, you are going to get 103 kilojoules plus 103 kilojoules. B. Option number B. So this is the delta H naught for the reaction. Okay. Got it? So option number B is the answer. Okay. Standard enthalpy and standard entropy changes for the oxidation of ammonia at 298 Kelvin are minus 382.64 kilojoules per mole and minus 145.6 joules per Kelvin per mole, respectively. Standard gives energy change for the same reaction at 298 Kelvin is. So standard enthalpy is given. Okay, standard enthalpy and standard entropy is given for the oxidation of your ammonia. Okay, so the entropy, standard enthalpy and entropy is given. So you have to find the standard Gibbs energy change for the reaction. Okay, so what is the standard Gibbs energy change? So change in Gibbs energy is equals to delta H minus T delta S. So this is the change in your standard Gibbs energy change. Okay. So standard Gibbs energy change is equals to change in enthalpy minus temperature into change in entropy. So change in enthalpy, what is the value? Change in enthalpy is minus 382.64 minus temperature is what? 298, 298 into. Okay. Change in entropy is, what is the change in entropy? Minus 145.6. Okay. Minus 145.6. So your kilojoules is there and your joule per Kelvin is there. So to convert into kilojoules, I will multiply it by 10 raised to minus 3. Okay. So this is kilojoules and this is joules. So I have to convert it into kilojoules. So I will multiply it into 10 raised to minus 3. So solve this. So after solving, so first multiply this 298 into minus 145.6. Okay, into 10 raised to minus 3. So after solving, I'm going to get the answer, final answer as 339.3 kilojoules per mole. So this answer you have to get. Final answer. This is the change in Gibbs energy. Change in Gibbs energy minus 339.3 kilojoules per mole. So if they ask you the Gibbs energy, okay, standard Gibbs energy change. So this is a formula which you have to use. So minus 339.3 kilojoules per mole. Got it? Okay. Let us go for the next one. A reaction occurs spontaneously if, so a reaction will, for a spontaneous reaction, we know that what will happen? Delta G should be always negative. Okay. So for a spontaneous reaction, delta G should be negative. So when it is possible, if delta S is positive and delta H is positive. So if delta S and your delta H is positive, then your delta G will be negative. That is T delta S should be greater than your it should be greater than the change in enthalpy. Okay, so because we know that change in Gibbs energy is equals to delta H minus T delta S. Okay, so for a reaction to be spontaneous, so delta G should be positive, delta H should be positive. Then if this positive, then this will be negative. Okay, so which is the answer? So option number, so your delta, this should be more. Okay, so this should be more, then this should be negative. Yes, so option number C. So delta T, temperature change in entropy is greater than delta H, that is change in enthalpy, and both delta N and delta H should be positive. So this is the uh, reaction. Okay, so if a reaction is occurring spontaneously, so this is the equation. So these are the condition which has to be followed. Okay. For vaporization of water at 1 atmospheric pressure, the values of delta H and delta S are 40.63 kilojoules per mole and 108.8 joule per Kelvin per mole respectively. The temperature when Gibbs energy change for this transformation will be 0 is. So the vaporization of water, okay, at 1 atmospheric pressure, the values of delta H and delta S are given, okay, change in enthalpy and change in entropy. So you have to find the temperature when Gibbs energy for this transformation will be 0. So Gibbs energy also is given as 0. So we have the formula delta G is equals to delta H minus T delta S. Okay. So what they have said at equilibrium, okay, at equilibrium, we know that delta, that is delta G will be 0. So at equilibrium, your Gibbs energy change will be 0. So put the values. So delta G is 0 is equals to change in entropy, change in enthalpy. So what is happening? Your water, okay, which is liquid, is getting vaporized to gas. So your liquid water is getting vaporized to gas. Okay. So what all is given? Let us write first. Delta H is 40.63 kilojoules per mole. So if you are converted into joules, it will be what? 40630, right? Joule per mole. So this is converted into joules. Then delta S is what? Because your delta S is in joules. So 108.8 joule per Kelvin per mole. Okay. So 108.8 joule per Kelvin per mole. So we have this equation delta G is equals to T minus delta S. Delta G is equals to delta H minus T delta S. So when your delta G is 0, okay. So if this is 0, then your delta H minus T delta S also will be 0, right? So T is equals to what? So if I take this, only this equation, so T is equals to delta H upon delta S. Okay, so because we have to find the temperature, right? So T is equals to delta H upon delta S. So delta H is 40630 divided by 108.8. Find out. So So what all is given? Okay, so Gibbs energy is stated as 0. So this is 0. So delta G, this after substituting T is equals to, because we have to find temperature. Okay, because we have to find temperature. So temperature is equal to delta H minus T delta S is equals to 0. Because when G is equals to 0, so this will be equal to 0. So delta H, so T, take it this side. So this will go here. So it will be delta H upon delta S. Okay. So from this equation, so we will get the answer. What I am getting is 373.4 Kelvin temperature. Okay. Temperature is 373.4 Kelvin. 0.4. So when your water, okay, when your liquid water is getting vaporized to gas, okay, vaporization means what? It is getting converted into vapors, okay. So it is getting converted into vapors. So this is the temperature. So option number D, 62 answer is D. Yes? Okay. Next question. The heat of formation of methane at constant pressure is 18500 calories at 25 degrees Celsius. Okay, this is heat of formation of methane. So you have to find the heat of reaction at constant volume. Okay, so this is a reaction when a carbon reacts with hydrogen gas, giving you methane plus 18,500 calories. Okay. QP is given, that is 18,500 calories, and R is equals to 2 calories. So this, so you have to find what? The heat of reaction at constant volume. What will be the heat of reaction of constant volume? Yes. So what all is given? QP is given, that is 18,500. Okay, 18,500 calories. Temperature is given. What is the temperature? Temperature is 25 degrees Celsius. 25 degrees Celsius. When you convert it into what is that? Kelvin. So 273 will be what? It will be 298 Kelvin. So this is your temperature. Okay. Then R is given as 2 calories. Then change in moles. Number of moles is equals to, so the heat of formation of methane at constant pressure is this. So the heat of reaction is given as, so change in number of moles. So 1, so it is 1 minus 2 will be equal to minus 1. Okay. So find out the heat of reaction. So they have asked the heat of the reaction. So heat of reaction at constant volume. At constant volume. Okay. So QB is equals to QP minus delta nRT, right? So QP is given 18,500. Change in this is minus N into what is R is 2, temperature is 298. Find out 18,500. This will be plus 2 8s are 16, 2 9s are 18, 19, 2 are 4, 5. So plus it equals to 19096 calories. Option number A. So this is a heat of reaction at constant volume. At constant volume. Got it? Okay. Next question. The enthalpy change of a reaction does not depend on. So the enthalpy change of a reaction, it does not depend on what? Enthalpy change of the reaction. So this is based on theory based question. Okay, so when you see the enthalpy change of a reaction, it does not depend upon the different intermediate reactions. Okay, different intermediate reaction. It depends upon the state of reactants and products. the nature of reactant and product, initial and final enthalpy change of reaction, it does not depend on the different intermediate reactions. Okay, so option number C. So it does not depends on this different intermediate reactions. So option number C is the answer. Okay, fine. So these were some of the questions on the chapter thermodynamics. Okay, any doubts up to here? Yes, any doubts? So most of the questions. So most of the questions we have solved. Okay. Any doubts? If you have any doubts, you can ask me. Okay. So try to solve uh, much questions on this chapter. Okay. So if you find any book, okay, you can solve last year, previous year's questions also. So try to solve. So some are theory based, some are like based on the formulas. Okay, we have seen based on the formulas also some questions are there. So try to solve. Just I will remove the synopsis. Okay, just see once the synopsis also, whatever we have discussed. Okay, so these are the things which we have already discussed in the synopsis, right? So these were the different terms which are used. Okay, so what are the types of thermodynamic processes we have seen? Internal change, internal energy. What is internal change? First law of thermodynamics, enthalpy and enthalpy change. Okay, heat capacity, Hess law. Okay, spontaneous and non-spontaneous reaction, entropy. Second law of thermodynamics gives free energy. Third law of thermodynamics, right? So these are all the things, okay, so which are using this, okay, which will help us to remember the important points. So these are the important things which you have to remember from this particular chapter. Okay, I hope everything is clear. Fine. So by this we have completed the chapter thermodynamics. Okay, so in the next class we are going to see the next chapter, that is equilibrium. So before coming for the next class, please read something about equilibrium. So in equilibrium you have ionic equilibrium. Okay, uh, so equilibrium, okay, ionic equilibrium, and you're going to see the acid base concepts, okay, different acid base concepts. So different things are there. So please read before coming to the class. Okay, next class, please read about equilibrium. Fine. Okay, so by this, I shall end the session here. Okay, we'll meet in the next class. Thank you.